Hi class, the purpose of this video is going to be to cover what I call sequential kinematic equations, as well as the so-called Nuke-proof method of solving systems of simultaneous equations. So I hope that you get that information from this video. Let's first talk about the equations that we're going to be using today, because it turns out that there's quite a few of them, and they're going to be familiar but maybe a little bit simplified. So we're going to use the four kinematic equations, and as a reminder, we have V is equal to A times T plus V naught. And then the next one is X is equal to V plus V naught divided by 2 times T. Now we're not going to add the X naught on there. You know that typically we have an X naught here, but I'm going to say no. Don't include that whenever you're doing sequential kinematic equation problems, and I will tell you why. That's going to be true of the remaining two kinematic equations as well. Next one is X equals 1/2 A T squared plus V naught T, and then no X naught at the end. And then finally, V squared minus V naught squared is equal to 2AX, and once again, no X naught. Okay, so these collectively are your kinematic equations. But they're simplified. And they're simplified because we don't have an X naught in there. Okay. We're also going to use the old standby. X is equal to V times T. You might use a version that has an X naught in there. Again, omit the X naught. Always omit X naught for these problems that involve constant acceleration over a finite number of time intervals. So no X naught. And then there's another one that's a little bit weird that we'll talk about later. V1 equals V2. This might appear in a longer problem as some other subscripts. It might be like V4 equals V5. But they should typically be sequential numerical subscripts. Okay? But the point is that you have one velocity is equal to another. Very simple equation, almost trivial, but I promise you it's important in this derivation. Okay, only two more. Capital X, the total distance traveled, is equal to x1 plus x2 plus x3. If you have more terms, just add them on. But I'm just going to stop at x3 because it turns out that's what the sample problem we work on today is going to use. Capital T, the total time, is equal to t1 plus t2 plus t3. Those are your, I guess, 8 equations, and I'll try and work all of them in throughout this video. So you may wish to pause and verify that you recognize each one of these. All right. So let's take a look at the problem statement that I've laid out for you. I've transcribed it from the problem statement that we were using previously, but I've made a couple of minor adjustments to it so that it's hopefully a little bit more clear. A record of travel along a straight path is as follows. 1. Start from rest with a constant acceleration of 2.77 meters per second squared for 15 seconds. 2. Maintain a constant velocity for the next 2.05 minutes. 3. Apply a constant acceleration of negative 9.47 meters per second squared for 4.39 seconds. And then part A asks what is the total displacement for the trip, and B asks what is the average velocity for the trip. Okay, so I just ran through that super quickly. It probably would be a good idea to pause and rewind the video and play it back at a slower speed, or just make sure that you understand the problem statement and have it all properly transcribed before we continue. Okay. As first step in solving these problems, what I typically like to do is to graph velocity versus time. I'm going to draw my axes in gray because I don't even draw my axes every time. So I'll erase these in just a second. but it starts from rest. Let's take a look back at the problem statement. I'll highlight known pieces of information. I'll underline them in green here. So it starts from rest, which means v naught equals 0. It has a constant acceleration of 2.77 meters per second squared. I'll call this A1. It's the acceleration during the first time interval. And it's for 15 seconds, which is T1, the time spent in that first time interval. Maintains a constant velocity. I could underline this and say that A2 equals 0, but I'll just say you should recognize that constant velocity means 0 acceleration. But what is important is that I underline 2.05 minutes and say that this is T2, the time spent in the second time interval. In the third time interval, we have a constant acceleration of negative 9.47 meters per second squared. This is your A3. And 4.39 seconds. This is T3. Okay, so let's return to our figure here. I'm graphing velocity versus time. And it said it started from rest. And so initially at t equals 0, the velocity is 0. Pretty straightforward. Okay, now it accelerates at 2 point something meters per second squared for some length of time. This figure is not necessarily going to be in proportion. Don't worry about getting the proportions just right. Just get the overall shape. And over this first time interval, it's going to have an acceleration of a1, which is known, and it will last for a time t1, which is also known. But we don't know the displacement over this time interval, which I'll denote as x1. I'm going to put it in red. You may not have colored pens or pencils to work with, so you may just want to circle it to say, hey, that's a variable. I don't know what x1 is. It's not in the problem statement. It reaches a top speed of v1. We don't know what v1 is. That's in red as well. I don't see it anywhere in the problem statement. And then it maintains a constant velocity for some time. And that time is t2. If you would really like, you could write a2 equals 0. But I'm not going to do that. So I'm just going to write t2 there. It's going to, in the second time interval, cover a certain displacement that we don't know. That'll be x2. So I'm drawing it in red. T2 is known. It's in the problem statement. V2 is the speed at the end of that time interval. You may say, well, V1 and V2 are the same. Why do I need a new variable there? Turns out it's just better for your subscripts. I promise you, if you were to call this V1, then your subscripts would get really, they would kind of be offset from one another. You would have them not matching up the way that you really want them to. After that, it decelerates, or has a negative acceleration for a known time interval. So it has acceleration a3. That covers time interval t3. Those are both known. What is unknown is the displacement over this time interval, x3, and the final velocity, v3. All right, so this is, I think, a very succinct way of representing all of the information in the problem statement. I'm going to take this opportunity to erase my axes. So if I present a diagram like this in class, you should know what it's referring to. Okay, so yeah, we know A1 and T1, T2, A3 and T3, and our unknowns, again, if you're going to circle them, are X1, V1, X2, V2, X3, and V3. It is super easy to write other problem statements where other variables are known. So I could give you X3 in the problem statement, and I could take away T2 or something like that. Something along those lines, or take away T3. That might be a safer bet. Okay, there's two more variables that we need to take into account that so frequently show up in these problems. In fact, I think they show up in basically every problem statement of this variety, that I'm going to list them down here: capital X and capital T. Okay, capital X represents the total displacement. That's the displacement over this entire journey. and capital T represents the total time spent on this journey. Capital T is super easy to calculate. It's just T1 plus T2 plus T3. All three of those are given, so that's simple enough. But capital X, we have some intermediate steps that we need to solve x1 and x2 and x3 first. Note that x1 represents only the displacement over this time interval. Okay, x2 represents only the displacement over this time interval. When I said you're going to omit x naught from your kinematic equations, that's what that represents. It says I'm not going to take the initial displacement for the second leg of this journey as x1. You could do that. I'll tell you that it works out, but I'll just say that there's enough ways to write these problems such that isn't the case, that such that you don't want to do it that way, then I'm just going to say don't bother. Don't add on the previous displacement. Just concentrate on the displacement over each time interval individually. Okay, so here's the overall strategy. For every diagonal leg, we're going to get two equations, and those two equations are going to be two kinematic equations. For every horizontal leg, you're going to get two equations, and those two equations are going to be distance equals rate times time, x equals v times t, and then v1 equals v2, which you can see is going to explicitly show up here, v1 equals v2. And then here's another diagonal leg, so we're going to use two more kinematic equations. And then finally down here, we're going to use those last two equations. Capital X is equal to x1 plus x2 plus x3. Capital T is equal to t1 plus t2 plus t3. Okay. Add all of those up. I see two equations here, two equations here, two equations here. That's 2, 4, 6, and then two more equations down here for capital X and capital T. It's a total of 8 equations. If we were to solve for all of these variables, and I promise you that we can, we would need 8 equations to solve for all 8 variables. 1, 2, 3, 4, 5, 6, 7, 8 variables, and so we're going to need 8 equations to solve for all of them. I'm going to show you that we can be a little bit clever and not actually solve explicitly for all of these variables. So in particular, I'll just tell you that V3 we can ignore entirely, and T we can semi-ignore, but I'll throw it in there because it's not too difficult to work with. Okay, so I have an example of some equations that you might use. You're going to look at this first time interval. Oops. You're going to look at this first time interval, and you pick two kinematic equations. Doesn't matter which two. Pick whichever two you like. So I'm going to pick ones that are probably not well suited for solving this problem. x1 is equal to v1 plus v naught divided by 2 times t1. That is a perfectly valid equation involving the variables that define this time interval. Okay? We've got v1, our final velocity, v naught, our initial velocity, and t1, our time interval. At some point, we can erase v naught because, hey, v naught equals 0. Okay? Here's a second equation, second kinematic equation that we can use. v1 squared minus v naught squared is equal to 2a1 x1. That's valid. That works. And those are the only two equations that we need for this sloped portion. The reason why is because any two kinematic equations can be used to derive the other two. And so that's as much information as we could possibly wring out of that first time interval. What I'm going to do in a little bit later is choose some different kinematic equations that are going to get you to the solution a little bit more efficiently. So just keep that in mind. For the second time interval, we see that there's a constant velocity, and so these are actually some nice straightforward equations that shouldn't be hard to remember or to work with. x2, our displacement over that time interval, is equal to v2 times t2. The subscripts all match up. And v1 v1 is equal to v2. Our two velocities match. So that's just your familiar displacement equals rate times time over this time interval, which is true because there's zero acceleration. And it's saying that these two velocities are equal to each other. We need that equation in there to have 8 equations for our 8 variables. So don't skip over that. It may seem trivial, but you absolutely do need it in there. Okay, now let's move on to the third time interval. I'm going to pick 2 more kinematic equations that are relevant there. So I've chosen V3 is equal to A3 times T3. And x3, our displacement over that time interval, is equal to v3 plus v2 divided by 2, which is our average velocity, times t3. Again, doesn't matter which 2 kinematic equations you use. I picked some really crappy ones, so probably don't want to pick these same ones. Finally, don't forget our last 2 variables down here and their corresponding equations. The total displacement is equal to x1 plus x2 plus x3. And t, capital T, is equal to t1 plus t2 plus t3. This is saying the total distance traveled is equal to the distance traveled in the first leg plus the distance traveled in the second leg plus the distance in the third leg. I should say displacement in the first, second, and third legs. And the total time spent is the time spent in the first interval plus the time spent in the second interval plus the time spent in the third interval. Okay, so these now are 8 equations, and I didn't introduce any new variables. It only uses the symbols that you see right here, and I see 8 symbols in red, and so I know that I have 8 equations and 8 variables, and in principle it's solvable. Okay, so that's really what I primarily want you to take from this class. We're going to work as efficiently as possible to get a solvable system of equations, even if solving it might be very difficult for you. And for some of you, it will be difficult. But if you follow the Nuke proof method, which I'll cover in a minute, you shouldn't have too much trouble with it. You should get much better at it throughout the course of the semester. Okay, before we do that, let me talk about a better system of equations that we could use to solve the same problem. So let me copy my figure here, just to have it on hand. So primarily, I want you, if you have, as is the case here, a system of 8 equations and 8 variables, primarily I want you to get the equations on the page. I don't care which equations they are, I just want it to be solvable. It's more of an art form, however, I really do mean that, it's more of an art form to divine which equations are going to be the best ones to use. So I see that we have A1 and T1, and we really are going to need X1. So let me write x1 equals 1/2 a1 t1 squared plus v naught t1. But v naught is equal to 0, so we'll erase that in a minute. Now we have x1 in terms only of known quantities. We'd also need v1. We're going to need v1 before we can solve the rest of this problem. So v1 is equal to a1 t1. Again, it's written only in terms of known quantities. Our middle 2 equations stay the same. These 2 equations are always the same no matter what problem you do. As long as you have a horizontal region, you need to use v1 equals v2 and x2 is equal to v2 t2. We have the third leg here, and this is where I'm going to be a little bit clever. I'm going to use just one kinematic equation. I'm going to use x3 is equal to 1/2 a3 t3 squared plus v2 times t3. You got to be careful because v2 is the initial velocity for this third time interval. So that has to be the velocity that we plug in there. And then finally, I'll use the same two equations for the total displacement and the total time. The reason I can get away with using just one kinematic equation here is because the problem statement doesn't ask for V3, and we don't need V3 to solve for anything else. That's what makes choosing the right kinematic equations an art form. So capital X equals x1 plus x2 plus x3. Capital T equals t1 plus t2 plus t3. And that's it. So in the second half of this video, we're going to cover what a previous student of mine called the Nuke-proof method of solving systems of simultaneous equations. This is really just a substitution method, but you're going to lay out your information really carefully. Do it really deliberately, just the way that I tell you to. For a simple problem like this, it's not going to be so bad, but for other problems that you see, you're going to be really glad that you have something that is nuke-proof. Okay? Let's take a quick look at these equations one more time. So you'll notice that we have 7 equations and 7 variables. Our 7 variables are x1, x2, x3, V1 and V2, but not V3. We've omitted that. You'll see that V3 doesn't show up anywhere in these equations. And then capital X and capital T, both of which are, at least in principle, unknown. I know that you can calculate capital T very easily, but we're going to treat it as a variable regardless. The substitution method that I like to use, the way that I do it is I like to pick an equation. It does not matter which equation you pick, but I just suggest that you pick a simple equation, and the simplest equation I see is V1 equals V2. One velocity equals another velocity. You're going to use that equation to solve for one of your variables. Doesn't matter which one I pick, but I'm going to be a little bit sneaky and pick V2. Oops. Pick V2. And I've solved for V2 in terms of V1. I'm going to underline that equation because it's very handy. And I'm going to cross out the equation that it came from because I can't use it again. I every now and then get a student who wants to substitute this equation back into that one, and you can't do that. So that's why I say cross out this equation. Now, everywhere that I see V2, I'm going to replace it with V1. So let's take a quick look at our equations here, and I see a V2 right here, and I see a V2 here. I'm going to replace both of those with V1. But one of the things that students like to do, and I'm going to tell you not to do it, is skip equations. I want you to rewrite equations even if they don't change. So I get x1 equals 1/2 a1 t1 squared. Plus v naught t1. And I think now is probably a good time, sorry to tell you this a little bit late, now's probably a good time to make use of the fact that v naught is equal to 0. So what I'm going to do is I'm going to go back to our original set of equations, and I'm just going to erase all instances of v naught. You could leave it in there, it doesn't make the problem a lot more complicated. And that's the only instance of v naught that I see. Okay, so x1 equals 1/2 a1 t1 squared. v1 equals a1 t1. We can't use the third equation. We've already solved for one of its variables. x2 equals v2 t2. But we need to substitute in for v2. So x1 equals v1 t2. x3 equals 1/2 a3 t3 squared. Plus v2 t3. But v2 is equal to v1. That's the substitution we're making. All right. And I believe we have 2 more. Yep, it's our total displacement and total time equations. Capital X equals x1 plus x2 plus x3. Capital T equals t1 plus t2 plus t3. All right. Now, if you look carefully, go ahead and pause the video if you want, But if you look carefully, you should see that we have 6 equations, and I bet you we have 6 variables because we have eliminated v2 from these equations. So if someone were to walk in on this class late, or because this is a YouTube video, if someone were to start this video late, they would say, hey, I don't know what you're doing, but I see 6 equations and I see 6 variables, and so I know that this is a solvable system of equations. We're back basically to the starting point in the sense that we can just repeat the step that we just took, or the steps that we just took. So that means we pick an equation that we like. I like v1 equals a1 t1. Pick a variable in that equation. Well, a1 and t1 are both known, so I'm going to use v1. I'm going to solve for v1 in terms of a1 and t1. Yeah, I just rewrote the same equation, but I really want you to do these steps methodically. Again, for these simple problems, you're going to drag your feet. You're going to say, oh, do I have to do it? Strictly speaking, no, but you know, it's really good habit to get into, and I'm going through the trouble of doing it, so you should too. So, where are we making the substitution? I see v1 right here, I see v1 right here, I don't see v1 anywhere else. So, rewrite all of your equations. x1 is equal to 1/2 a1 t1 squared. Yeah. x2 is equal to v1 t2, but we're making this substitution. v1 equals a1 t1. So a1 t1, and then that's multiplied by t2. Our next equation is x3 is equal to 1/2 a3 t3 squared plus v1 t3. v1 is equal to a1 t1, so that's going to be a1 t1 t3. All right. Capital X is equal to x1 plus x2 plus x3. Capital T is equal to t1 plus t2 plus t3. Okay, so you should be rejoicing that we now have reduced it to 5 equations and 5 variables. Again, I'm going to go slowly and methodically. When you get really good at this method, you can make the 3 substitutions that you see right here all at once into capital X. But I want you to see this method in all of its gory detail because it will save your life in this class and subsequent classes and in your other classes, in your math classes, in biology and chemistry classes. This is a really, really efficient way of solving problems, or very, what should I say, very way you can confidently solve problems and be satisfied that you've done your work correctly. So I'm going to solve for x1 is equal to 1/2 a1 t1 squared. Cross it out. Substitute it in wherever I see x1, which is right there. Rewrite all of my equations. x2 is equal to a1 t1 t2. x3 is equal to 1/2 a3 t3 squared plus a1 t1 t3. Capital X is equal to, we're making that substitution, 1/2 a1 t1 squared plus x2 plus x3. Capital T is equal to t1 plus t2 plus t3. Pick an equation. I like that first one. It looks nice and simple. Solve for x2. It's the only variable in that equation. Cross out the equation, substitute it in wherever we see x2, which is only right there. So you get x3 equals 1/2 a3 t3 squared plus a1 t1 t3. Capital X is equal to 1/2 a1 t1 squared plus x2, which we had was a1 t1 t2. Capital T is equal to t1 plus t2 plus t3. 3 equations and 3 variables. Going to solve for x3. And x3 is equal to 1/2 a3 t3 squared plus a1 t1 t3. Cross this out. And then, oh, I forgot a term. So capital X I had was 1/2 a1 t1 squared plus x2, which was a1 t1 t2, and then I dropped this x3 term. So go ahead and change that in your notes. Plus x3. Okay. If I didn't have that in there, I wouldn't have any place to substitute in this x3, which we just solved for. So I need to substitute it in right there. Notice, by the way, and this is a big deal, you want to work down the page. You don't want to work left to right, you want to work top to bottom. If you need more pieces of paper, that's perfectly fine. But you should see that my work is very clear so far. Capital X is equal to 1/2 a1 t1 squared plus a1 t1 t2 plus what we substitute in for x3, 1/2 a3 t3 squared plus a1 t1 t3. Capital T is equal to t1 plus t2 plus t3. Now, in general, what you will be working towards is one equation and one variable. In this instance, you actually are going to leave it with 2 equations and 2 variables because these, our last 2 variables are capital X and capital T, and those are independent of one another. So they don't communicate with one another, and we have capital X in terms of known constants, which you should be very happy about, and we have capital T in terms of known constants as well. Again, let's just review the work really quickly. I start with 7 equations and 7 variables, 6 equations and 6 variables, 5 equations and 5 variables, 4 equations and 4 variables, 3 equations and 3 variables, 2 equations and 2 variables, and for another problem I might have 1 equation and 1 variable. But this work is really easy to follow and really easy to check. And I get sloppy with my algebra too. When I'm working on scratch paper, you know, I'll have like an equation over here, and then I'll solve for a variable over here, and I'll maybe substitute it back in over here, and then write in another equation down here. And, you know, that's fine if you're working on your own, if you're confident in what you're doing, but if you're not confident in what you're doing, use my method. And even if you are confident in what you're doing, your professors are gonna hate you for doing it this way, for being sloppy. And they'll love you for doing it my way because they'll say, oh, I know exactly what this guy is doing. They're using the substitution method, and they're using it in the most easy to follow way that they possibly could. Okay, so all that remains now is to plug in numbers, and I'll be happy to do that in the last portion of the video. So it's just occurred to me that there's one more thing that I should talk about, and that's back substitution. This isn't a very good problem for demonstrating it, but I would like you to at least see how you might use it in another problem. We have now capital X and capital T in terms only of known constants, and if you look back here, in principle, lowercase x3 could be written in terms of capital X and capital T and some constants, and so what you would do if the problem statement asked you to solve for x3 as well would be to plug these expressions back in wherever you see capital X or capital T in your x3 expression. Then you would take those last 3 variables that you had solved for and plug them into the previous expression back here. And in general, you just work your way back up until you've solved for all the variables that are asked of you in the problem statement. So that's another handy utility of this method, is that you can very efficiently back substitute back up. I'd like you to do that algebraically. Many students prefer to do it numerically. Just be aware what your professor is asking for. Some professors really insist that you work algebraically. And I, for one, am among them. I will tell you to work algebraically whenever you can. And you can see that I've done this entire problem algebraically. So because we've used all of our algebra and found our solution in terms of these known constants, which I've represented symbolically, all that remains is to plug in values. So let's take a look back at our problem statement. We had A1 equals 2.77 meters per second squared and T1 equals 15 seconds. Let's write those down. I'll still put them in green. So A1 equals 2.77 meters per second squared. T1 is equal to, I've already forgotten, 15 seconds. Don't forget your units in this case. It maintained a constant velocity for T2 equals 2.05 minutes. This is why you want your units in there, is because I gave it to you in minutes, so we're gonna have to use a little bit of unit conversion. And then in the third time interval, we have A3 equals negative 9.47 meters per second squared. And T3 equals 4.39 seconds. And so really all we have to do is plug these in to our values here for capital X and capital T. So for capital X, let's do this in black. Capital X is equal to 1/2 A1 T1 squared. And that's in meters per second squared and in seconds, so the units work out. We're going to get it in meters. Plus A1 T1 T2, 2.77 meters per second squared, times T1, which is 15 seconds, times T2. Now you have to be a little bit careful. We need to convert that into seconds. You should know how to do your unit conversions. But 2.05 minutes converted to seconds is 123 seconds. Okay. And 1/2 A3 T3 squared. I'll put that on the next line. 1/2 times negative 9.47 times 4.39 squared. And A1 T1 T3 is our last term. 2.77 times 15 times 4.39. And that is equal to, and you'll have to give me a moment, okay, I hope I've entered this correctly, but the answer that I get is 5,510 meters. Okay, so there's your answer for part A. Part A asked for, if you go back to the problem statement, Always want to return to the problem statement to make sure that you're doing the right, doing what they asked of you. Find the total displacement. That's capital X. Capital X is the total displacement. For part B, we're going to find the average velocity. We don't have that among our variables, but we have the next best thing. We're basically one step away from it. So I could have included the average velocity for the entire trip among the variables that we solved for, but I chose to omit it because it's pretty straightforward. V average, or average velocity, is equal to capital X divided by capital T, the total displacement divided by the total time, right? That's the average velocity for the entire trip. It's the displacement for the entire trip divided by the time that the entire trip took. So we have that except for capital T. We need to calculate that first. Capital T is equal to T1 plus T2 plus T3. We have all three of those numbers. Those were 15 and 123 and 4.39. Yeah. And I'm going to be a little bit sloppy with my significant figures, kind of. And I'm gonna put too many significant figures on, so bad me. But I get 142.39 seconds. Okay? That's our capital T value. Now all that remains is to find V average, which I represent as a V with a bar over it. Capital X divided by capital T. And that is 5510 divided by 142.39. And the value that I get is 38.7. And that's meters per second, because I had capital X in meters and capital T in seconds. So 38.7 meters per second is your average velocity for the entire trip. So again, we were asked for the average velocity and we just found it. And so that is a complete problem for you guys. Looking back on this long derivation, which was actually not all that long, not as long as it looks. Looking back on this long derivation, I would like you to see that we were done with the physics at this step, where we had 8 equations and 8 variables. This was all of the physics that we needed to solve the problem. The rest is algebra, it's just math. And so I want you, as best you can, to separate the physics from the math, and to do all of your physics up front if you can. We then chose a slightly easier system of equations. Again, that's an art form. That's not something that I'm going to expect you to do perfectly every time. But certainly the lion's share of your points are going to come from picking an appropriate set of equations for a physics problem. Then we have this long derivation, which is all just algebra, and it's all the substitution method in this very nice systematic format. And we get some numbers coming out at the end. We plug in some numbers at the very end to satisfy the problem statement. But again, for the purposes of this class, and I hope for your other classes, I'm really going to be looking for, do you have as many equations as you have variables? And are those equations correct? If you can find 8 correct equations and 8 correct variables, that's going to get you more than half your points on an exam or other problems that you do. It really is by far the most important thing. But, you know, it's also not a very satisfying solution. You can see that you're you know, sometimes 10, 20, 30 minutes away from an actual answer, and that's because there's a lot of algebra. There's a lot of algebra in between you and your final answer. So, please take from that whatever you will. If you like this method, that's great. If you don't like either of these methods that I'm pushing on you guys, you know, maybe put up with it for a semester, maybe go your own way. I don't encourage it. I really want you to try to force yourself to do it this nice systematic way that I've laid out for you, because I've put a lot of thought into it, and it's you know, maybe not perfect, but it's the least bad way that I've come up with after all studying that I've done. So thanks for watching, and I will see you next class.